Hello, welcome to lecture 5 of this course. In this particular lecture, we're going to look at nonlinear algebraic equations. First, we're going to look at fixed point iterations, and then we're going to look at Newton iterations, and finally, we're going to look at basins of attraction for the Newton's iteration. And while many of these things you may be aware, there's a few lectures by in NPTEL itself. The links will be there in the description. And the point of this lecture will be to visualize how fixed point iterations converge or how Newton's iterations converge. And hopefully you'll pick up a thing or two on how to encode everything in Python. Let's begin. So first things first, let me import numpy as np. Let me import matplotlib.pyplot as plt. Let me change the inline configurator. So plt.rc params.update. Inside this we will use text.use text true, and the inline config inline backend dot figure format equal to svg. So once we're done, let us begin by looking at the fixed point iteration solution for the equation exponential of minus x, or rather exponential of x minus 3x square equal to 0. So we're interested in solving this nonlinear equation, and let us see how we can do that. So in fixed point iterations, the target is to cast the equation in the following form. And the way to numerically do this is to make some guess value, say x naught. So using this guess value, you find out f of x naught. You assign it to x1, then you find f of x1. You assign it to x2, then you assign it to f of x2. So ideally, if we have the root, or rather we have the solution of this nonlinear equation, then x on the left hand side would be equal to the function of x on the right hand side. For example, this particular equation, we have exponential of x minus 2x square equal to 0. So we can write it in the following form: exponential of x equal to 2x square, and we can rearrange this to write it as this. So x equal to exponential of x upon 2x. So if x is the solution, then left hand side and right hand side would converge. But if x is not the solution, there would be some error, and these set of iterations are what are driving us towards the root. And at the end of this particular section, it would be clear how the iterations do converge. So before that, let us quickly have a look at how the function actually looks like. So let me define x equal to np dot linspace minus 2 to 5, y equal to exponential of x minus 3 times x square. So let me do a plot, plt dot plot x comma y. So let us adjust the limits in the y direction. So plt dot ylim will make it minus 2 to 2. Let's see. Yeah. So let us draw a vertical line through 0. In fact, let me just make the limit from 0 to 2. So the intersection of the curve with the x-axis happens at these points, and obviously these points are roots of this particular equation, because at these points the whole equation is equal to 0. All right. So let us see how we can. Let us see one strategy of doing this. So we can do the following. We have exponential of x is equal to, is it 2x square or 3x? It's 3x square. So exponential of x is equal to 3x square. Let us take a log of this. So we have log of exponential of x. So essentially it will be simply x is equal to, so log of this will be log 3 plus 2 log x. Alright, so the iterations would look something like this. The k plus 1th value of x will be derived from the kth value of x. So this is how these iterations are going on. So it's quite easy to encode. You can imagine that you just need to run a loop. You just need to set a number of iterations and run a loop. Okay, set iterations, and inside this loop you will do an update of the value of x. So this is the particular update, and obviously you'll enter the loop with some value of guess. All right, so let me do that. So let us first define the guess value. So x naught is equal to, so let us take a guess value between this. Let us take a guess value over here. So let x naught be equal to 2. All right, so let us define the number of iterations. So n iter equal to say 50 or 20, doesn't matter. So for I equal to np dot a range 0 to n iter, we would do x is equal to np dot log 3 plus twice np dot log of x. So this will be x naught because it's entering the loop with x naught, and once we have the value of x, we'll assign x naught the value of x. So in this way, by the time we converge, x naught would have the final value. So let us finally print x naught. All right, so let me execute this. So this is a syntax error. Okay, so it gives us a value of 3.7330. So something close to this. All right, so let me do one thing. Let me make this into a function. Okay, so I will define fx, which will take as an input x, and it will return this. Okay, so here I will simply call x naught, and it should have the same result. So it increases the readability of the program. Okay, in fact I could have simply done this. Don't need to do all this, and I would have the same answer. Now suppose I want to visualize how the values of x have evolved. Of course I can print all the values of x naught in the loop itself, and this is how the iterations look like. So we started with a guess value of 2. After the first iteration, this is how the value of x naught has been updated using this particular function. So each successive iteration leads to a correction in the root, and eventually we do get a convergence. Okay, so now we can actually store all these values in case we want to plot them. Okay, so let us define x equal to np dot zeros and iter. So it will initialize an array. All of the elements of that array will be 0. So this is initialization. Then we will assign the first value as x naught. All right, so here we will make the loop go from 1 to n iter because we already have the 0th value, and here instead of passing x naught we will pass xi minus 1. So this modification to the code has the same effect. There's nothing new that we have done to the code. And finally, we'll print out the value of x. There you have it. X is now an array and x contains all the values. Now let us see how the convergence has occurred. So plt.plot. So we need the iteration number. So the iteration number will be simply np.arrange. This will go from 0 to an iter, and on the y-axis we'll plot x. So we've started with a guess value of 2, and eventually we've converged towards this root 3.73 whatever. Okay, now suppose someone asks, well, does it depend really on what the guess value is? And we can repurpose this code to find that out. So let me copy this bit of code. Let me make this a markdown cell and let us write down what we're trying to do. So let's see the influence of the initial condition on the convergence. Alright, let me paste this. So this particular guess value has to be also run in a particular loop. Okay, so how can we do that? Okay, so let me define f let me define everything inside a function. Let's say we call it perform iterations. Okay, and inside perform iterations we'll have a for loop, and it will return x, and the function should take as an input the guess value. Inside the function we will initialize all this inside the function, and we don't need n iter anymore, because we can pass n iter to the function as well. Suppose you want to test out how many iterations, what does the iteration number look like. So let us pass it to the function perform iterations as well. Okay, so this particular function will take the guess value and the number of iterations that we want, and it will return us the sequence of how x converges. Okay, so let us define a value of the guess values. So x0a is the array which contains the guess values, is np.linspace, and let's say the guess values are, let's have a look. Suppose they go from 1 to 3.5. Suppose the guess values go from 1 to 3.5, and let's say we take 20 guess values. Okay, so for x0 in x0a, we will call the function perform. So we will assign it to x, and we will say perform iterations x0 comma n iter, and we have to define n iter. Let it be 20 at the moment, no problem. At the end of it we'll plot plt.plot np.arrange 0 n iter comma x. It's the same plotting function. So let's run this and see what happens. Alright, we have a bunch of curves for each starting point. Alright, and it is seen that after 13 iterations everything converges. Okay, for each starting point we have made the plot, and it is quite apparent that the initial values do converge to the value of 3.73, whatever it is. In fact, let me increase this particular range. Let me make it till 5. Let us go above the converged value. Okay, so even if you guess it beyond this particular point, you seem to converge. All right. So if we have this is the figure, right? So we have, if we guess over here, we still converge over here. If we guess over here, we still converge over here, which is great. But what about these two roots? Okay, we don't seem to have we I mean, even though we are starting at a point which is quite close to 1, we don't even if we start over here, we are not converging to this particular root. We're in fact converging to this particular root. Okay, so let us see what the effect of rearrangement would be. Okay, so by rearrangement I mean, instead of this, let us use this. So over here we had, let me in fact erase this. Let us do a simpler rearrangement. So let me rearrange this to x equal to 1 by square root of 3 exponential of x by 2. So this is one more rearrangement that is possible. Alright, so let us go back to our program. Let me copy this bit of code. I mean, we can of course reuse it because we have wrapped the RHS into a function. We don't need to redo many things. We just need to change the functional form. Everything else remains the same. Alright, so this will be second kind of rearrangement. Alright, so let us go ahead and change the return value. So this will be 1 by square root of 3 times exponential of x upon 2. Alright, okay, so let us take the guess value as 2, no problem. So let us run this. Let us see what happens. Okay, so we started at a guess value of 2 and we've converged to a value of 0.91, whatever it is. Let us see whether that is true. So 0.91 is actually the second root. So by changing the type of rearrangement that we have, we seem to converge to the second root. Okay. So far we've seen two cases. I'm not going to elaborate on this any further. These are fixed point iterations for this particular function. Let us have a look at a different kind of function, and it will demonstrate as to how this procedure doesn't always work out. There may be cases where you'll never converge. Let's see. So let the function, let me write down the function. So it's exponential of minus x minus 3x equal to 0. Alright, so let us plot this function. Alright, so x equal to np dot linspace minus 2 to 5 minus 2 to 4, y equal to exponential of minus x minus 3x. plt dot plot x comma y. Alright, this is how the function looks like, and let me set the y limit. Plt dot y lim this will be 0 comma 2, for example. Okay, so we do have a solution over here. It looks like something 0.2 something. Okay, so let me repackage this code and let us change this functional form. So let us see two functional forms. So the first functional form it can be x equal to 1/3 exponential of minus x. Now that's a very straightforward looking functional form. Well, let's have a look. So 1/3 times exponential of minus x. So let me run this. Well, that's great. We do converge to a value of 0.25. It does visually look like it's a root. And there's an easier way of checking whether it's a root. Let us print fx of x n iter minus 1. Essentially, I'm trying to check the last value. Okay, fx. So the value of x and the value of this, they do match. In fact, let us print this also. Ah, sorry. Okay, so it does say that initially they are not close. Okay, initially they are not close, but as we go towards, so this array shows it is checking this particular value with all these values, with all the arrays of x, and after a certain point in the iteration sequence, they become close, and that's why we start getting true. Okay, this is how you can do a quick check. Anyway, so mm, let us try to do another rearrangement of this. Okay, let me copy this code. Let us do a rearrangement which is also quite trivial, to be honest. Let us take this 3x and let us split it into 2x and x. Let us take one of the x on the other side. So consequently, we will have this. So this is also an expression for fixed point iterations. So let us reformulate the function. All right. Okay. So when I execute the cell, it seems that initially the value is 2, then something happens and then it flies off into infinity. Okay, it flies off, it doesn't converge. In fact, let us plot these two sequences. Okay, let us try to plot these two sequences. Let me copy this. Oops. Let me call this gx. So gx converges, and this function appears to diverge. So let me create another array xx. So np dot zeros and iter, and xx0 also will be x0. So I will run a single loop, but I will perform the two iterations side by side. Okay, I am performing the two iterations for the two different functions side by side. Sorry, this should be I. All right. So it's showing an overflow error because it's diverging to infinity, but that's okay. Let us do the plot. So plt.plot np.arange 0 to n iter, comma x np.arange 0 and iter, comma xx. All right, let us see. Okay, so quite obviously the blue curve, it diverges quite wildly. This should be xx. Yeah, this was a small error because obviously it has to take its own array. Okay, this was a small error. All right, so let me replot everything. Okay, so let us change the while limit. So plt.whilen. Okay, So what we see is the iterations for the function for this functional form. It oscillates and then it converges, but for this functional form it oscillates and blows off to infinity. Okay, so I mean, it's quite obvious while programming a bit fast you are prone to making mistakes, but that's okay. Try to pay attention, don't do the silly mistakes that I do. Let us now try to visualize how these iterations actually look like. Okay, so let us go back to our initial example, uh, this particular example. Okay, so let us um, let us make the number of iterations 10, and let me again define the same thing, x equal to np dot zeros in iter, then x guess as 1.1. I mean, this can be changed during the course of the program. Let me define fx as return np dot log 3 plus twice of np dot log x. Okay, so we've defined the return value. So let us define yeah, so let us try to plot those two functions. Okay, let us try to plot something. So xp will be np dot linspace minus 2 to say 0 to 5, say 100 points. Yp is that actual function, so that function is exponential of x minus 3 into x square. All right, so let us plot this. So plt dot plot, actually this we don't want to plot this, we actually want to plot fx of xp. So let us plot xp comma yp, and we'll label it as the right hand side function, and we'll plot xp comma xp, and that is like the, I'll explain what it is. So let us do this. Okay, so once we've plotted this, okay, so let me make it from 1 to 5, 0.2 to 5. Okay, so what is really happening? Let me try to show it over here. So basically we have one function which goes like this. This is the RHS function. This function is the function y equal to x. All right, so suppose you make a guess value over here. So then what is the procedure that we're following? So x1 gets the value of f of x naught. But let me split this. Okay, so first thing you evaluate f of x naught. So this thing is the, so f over here is the RHS function. Okay, so this is f of x naught. So this particular coordinate is x naught comma f of x naught. Then you assign it to a new value. So this f of x naught gets a new assignment to a value of x. So this particular y, okay, this particular y value, okay, this y value is now mapped to a value of x. So the way to map a value of y to x is to drop a projection onto the line y equal to x. by virtue of y being equal to x on this line, this particular x value has now received the y coordinate of this. So this becomes f of x naught, which is by definition x1. So then we repeat. So then this is f of x1, this becomes x2. So this is f of x2 and this becomes x3. So you see, this is how the iterations are converging towards one particular root. Now you may say that, okay, fine. What if the curve does not look like this? The curve can actually look something like this as well, right? No problem. So this is the initial guess. This is going to be f of x naught. Then you project it to the y equal to x line. Then you project it back to this, do this, do this, do this, and you converge. So if the curvature is reversed, we see that it converges to the other root. All right. So let us try to encode uh, this particular sequence of steps. Okay. All right. So for I in np dot a range 1 to n iter, so we will do x new is equal to fx of x guess. All right. Then we'll do the plot. We'll make this particular point. We'll draw this particular point. So we will do plt dot plot, and this particular point, the x coordinate will be xg, right? The y coordinate will be fx of xg. No problem. We'll make it as a marker, and let's set the marker face color as black, and let us put the marker size as equal to 2. Okay, so now with this new x, we have to now map it to the other value. So x2, let it take the value of xn. All right, because this is the new x. All right, and y2 will be equal to simply x2. Plt dot plot x2 comma y2, and the remaining string remains the same. Okay, so essentially this particular plot is this point. I'm trying to plot this point. Okay, so x2 is having the y coordinate of this, so that is why this particular thing should give us this point. So the first plot is for this point, second plot is for this point. Then when it runs into the loop again, this will become the first plot, this point will become the second plot. Okay, so I mean, let's run this. Let's see. Okay, so okay, why is it giving me only 2 points? Because I have not updated anything, so I have to update the value of xg also. So xg should get the value of xn. All right, there you go. So the first guess is over here, it projects onto this. Then the second guess is over here, projects to this, over here, over here. I mean, it would be nice if we could join it by some arrows. All right, so it's quite simple. So we do plt dot arrow. This has to be done prior to the assignment of xg equal to xn. So plt dot arrow. So the first arrow has to be from x xg fx of xg to. So the syntax for arrow is xy delta x delta y. So this coordinate over here is xg f of xg, and this coordinate over here is x2 comma y2. So the first arrow has to be from xg f of xg, and the delta x will be x2 minus xg, and y2 minus f of xg. Alright, so let me do that. So this will be x2 minus xg comma y2 minus fx of xg. Alright, and there's a certain attribute of an arrow, that is length includes head, and we have to set this to true because the delta x has to also include the length of the arrow. So let me set the line width of the arrow to 0.7 and let the color be equal to blue. Once this is done, we can plot the second thing. So the second arrow will be projection onto the curve again. Okay, so this will be okay. I mean, let us have a look at how this looks. Okay, there's an error. Ah, this is typo. This is a small typo. Okay. Okay, so now we have drawn all the horizontal lines, and we just need to focus on the vertical lines, and that's quite easy because this particular point is equivalent to drawing an arrow from x2 y2 to x2 and f of x2. That's it. Okay, so we just need to copy this bit of code, paste it over here, and change these values. So x2, this will be y2, this will be x2 minus x2 because it's a straight line, and this will be y2 minus f of x2. And let me make this line as red. This is a small error because okay, this has to be f of x minus y2. Okay, there you have it. So this shows how the iterations converge. Okay, so now because we've already done how the iterations converge, let us change the function and see how the different choice of the iteration would look like. Let us go over here. So the different choice was this. All right, so this was what, 1 over 3 to the power 0.5 times np dot exponential of x upon 2. Fine. When we run this, we see that everything converges over here. Let us take a different guess point. Let us take a guess point of something close to 3.5, for example. Okay, so when we start at 3.5, we see that it converges towards the root at the bottom. Okay, and in the accompanying notes, which you will find on my website, I'll explain mathematically why this convergence happens in this way. Well, this is not a course of an exposition on the mathematics of it. I'm hoping that you would have seen the other NPTEL courses which deal with this kind of mathematics. I'm trying to show you how you can make the best out of the tools available to you to really understand the process that goes on behind the machinery. Well, we've seen the two cases where they seem to converge to a certain root. We did see a certain case where convergence was not there. In fact, everything diverged. In particular, this was the case in point. Let us have a look at how that particular set of iterations actually looks like. I mean, what causes it to diverge? That should be the question that comes to your mind. So let us see. Let us replace this by np dot exponential of minus x minus twice of x. Let us take the guess value of 0.25. Let us run this. Okay, something has happened. There seems to be a very large Let me take it from -5 to 5. Let us try to locate where the things have started somewhere over here. So let us change the limit. Let us keep it confined to 0 to 2, and let us keep the y limit confined also between -2 to 2. Okay, there we see the culprit. In fact, let us zoom into that further. And because I'm using Jupyter Lab, I don't have the interactive zoom at this moment, but you can look it up on the internet how to do that. But it won't be required for explaining this particular phenomenon. So, all right. Okay, so this is the guess value. So the guess value is 0.25. So it starts over here. Then it maps on to the x equal to y line. Then it maps on to the curve, maps on to the x equal to y line. And it seems that these sequence of iterations are going out of hand. They don't seem to converge. Let me try to pictorially motivate this. Okay, so we have the x equal to y line like this, and this is the curve. So this is the initial guess. It goes over here, then like this, then like this, so on and so forth. Well, I've drawn a much more compact version of what is actually going on, and this is the root. This is the point where y equal to x and y equal to f of x, they converge. Basically, when they become equal, it means x equal to f of x. So this is actually the root that we are aiming at. But even though we are guessing very close to the root, we see that the successive iterations are going out of hand. They're diverging very quickly to infinity. And the reason why this actually happens, and I'll put it up on the website as a side note, is the slope of f at the fixed point. So the fixed point, I mean the root. So df dx at the root must be less than 1. The magnitude of the slope must be less than 1. In this particular case, the magnitude of the root is obviously quite large. Okay, and for the other two cases, it is converging to the root where the slope of the blue curve is less than the slope of the orange curve. Here it is less, while in this case here it is less. So it is converging towards that root. Okay, and in case you don't have the condition in the curve where the type of discretization that you do, that is this particular form of discretization that you do, if it is not able to satisfy this condition that the slope at the root has to be less than 1, the magnitude of the slope has to be less than 1, if we are not able to achieve this, well, achieving this a priori is not easy because you don't know where the root is, but still graphically you should be able to figure out when this will converge or whether it will converge or not. Okay, so the accompanying mathematics is not extremely difficult. It makes use of a Taylor series expansion around the root. Okay, so now let us proceed. Let us look at how we can make use or make Python do all our work. Obviously these things are quite important for engineering, for mathematics, in general, for biology. Okay, if you're trying to study nonlinear equations like the Michaelis-Menten reaction, often you need to find out what will be the equilibrium product. So things like this you need to find out. So there are libraries to do that. So let us go over here. So most of the things are sort of in the submodule called as optimize in Scipy, and the reason why it is in the submodule Scipy dot optimize is because these root finding problems can be sort of recast into a minimization problem, and once you recast things into a minimization problem, you can sort of find out the minima. If it's a convex problem, we can find out the minima with the help of very sophisticated algorithms. That's why all these things lie in the optimized library. So we need to import the optimized library. So it will be scipy.optimize. Let us import it as sco. Let us define, okay, let me keep this in a separate cell. Let me define fx of x as the following. Return np.exponential of x minus 3 into x square. Let me define it like this. So this is the function that we've solved so far. Essentially, this is exponential of x minus 3x square equal to 0. So this is the return value. So now we will say sol. The solution is sco dot fsolve. We will give the function handle. So this is called as giving the function handle. You're telling fsolve that this is the function handle to from which you have to do all the iterations. So it does all the iterations internally, and then you have to provide the guess value as well. So let us give the guess value of 1, and in the end let us print sol. Let's see what happens. Okay, so it's giving us the converged value of 0.91, and if you recall, that was indeed one of the roots. In fact, when we choose a different initial value, we converge to the other root. In fact, if we choose another initial value, we converge to the third root. If you recall, there were 3 roots of this entire system. There were 3 roots. One was over here, one was over here, and one was, so depending on where you give the initial value, it will convert. So it tries to find out whether you have to take a positive slope or a negative slope. It has to keep the slope bounded. There's a bunch of algorithms that go on behind the scenes, but this is how you can minimally solve a nonlinear algebraic equation. There are many other ways of doing it. There's also a method called as Brent Q. Essentially, it is a bracketing method in which you need to specify the domain inside which you expect the root to exist. So okay, so if we give the initial, so depending on the bracket, it will give you the root that it encounters. It's a very useful method of finding out the roots. Lastly, I want to show you the famous method. I mean, it's called as the Newton iterations. So the way to do it is sco.newton. You have to give the function and 1. Let us print sol3. Okay, and depending on the initial guess, we have a different solution. And typically, for the Newton-Raphson method, we have to also provide the Jacobian. All right, so essentially it's the derivative, analytical derivative of this particular function. So fpx is the derivative of x, the analytic expression for the derivative of x, f of x, and we'll pass it to the function as well. So it converges much faster. In the second part of this particular topic, we'll be studying systems of nonlinear equations and basins of attraction for the Newton-Raphson method. That is, points on the complex plane which converge to a specified roots. And we'll see certain non-intuitive observations in the basins of attraction. So do join me in the next lecture. I'll see you again. Bye.